Hey everybody, thank you for coming tonight. As you can see on the screen and by the email we sent you, tonight we are working on probability. Hopefully Scott will get a chance to come on in about 30 minutes and do some stuff as well. And as always, I'll start. So for those of you that were here last week, we did some combinations, and I focused heavily really just on combinations. And as you may recall, or anyone who saw the recording of last week, I kept referring back to this idea that combinations and probability are pretty much interconnected in a lot of ways. And the way to be able to tell when can I use a combination within probability or use that method has to do with when the probability questions that's being asked could be easily converted to a combination question or vice versa. And, you know, one of the things I'll quickly mention here before we get started with some problems is this idea that probability, you know, what it actually is it's the favorable outcomes over the total outcomes. Now, we don't normally think in combination land when we're thinking of probability because we're normally thinking of, you know, fairly basic probability or something like, you know, what's the probability of getting heads when you flip a coin? Well, it's going to just be 1/2. The favorable outcome is the heads that you're trying to get, and the two total outcomes is heads plus tails. That's two possibilities, but you never really think about it like that, and that's fine because that's a really basic problem. But clearly, as these things get more challenging and there's more complicated, you want to have different ways of going about them, things that'll make you efficient, especially on 700 level plus type questions. One of the other things we talked about last week too is the idea of when you add versus when you multiply with combinations. And just like in combinations with probability, if you have multiple probabilities that are happening at one time, you're going to multiply them together. But if you have probabilities where the word quote unquote or is being used, or you're dealing with scenarios, you would end up adding. And you know, these are some small tidbits that we'll be using tonight. I am going to get into some pretty challenging questions, but I hope for those of you that were here last week and, you know, really got into the combinations based off of what I did, you're going to see a lot of similarities between that and what we're trying to do tonight. So I want to start off with a question here. This is you know, I'd say a mid-range probability question, something that I think will get us started pretty well. I'm going to show you eventually multiple ways in which you can solve it, and then we can kind of go from there and talk about the solution. As always, you know, you can put your answer in the chat box so I can see what everyone is getting, and that's about it. So we're going to do a lot of really good questions tonight. So we will start with this question here. Okay, so that was about 2 minutes there. And, you know, hopefully for those of you working through the problem, you felt like this is something that at least you could attack to a point where you could come up with an answer. This isn't the easiest question in the world, though. There are some nuances to it that if you don't know or miss, you can get it wrong pretty easily. So the first thing I'm going to do, I'm going to stay away from combos for the moment, and then I'm going to kind of bring those back in after I do this just using kind of a regular probability method. So a couple things to think about in any probability question, and this also dictates whether or not combinations or permutations can be used to solve it. But the first thing is when we're saying what's the probability of selecting a white and red marble, we see that there's 2 marbles being selected, so that's 2 attempts. The problem also does not say that the marbles are being put back, so you can always make the assumption that after you select 1 marble, it's gone from the possible number of marbles that you can select from. So the first thing I would say here is, okay, well, I'm going to say probability of white times probability of red. Now, we know that we have 5 white marbles, so the favorable outcomes is 5. Total outcomes is 12, as said at the beginning of the problem. So that's the probability of getting a white marble is 5 over 12. The probability of a red marble is 3, but now instead of out of 12, because it's the second selection, it's 3 out of 11. Now, the best thing to do here is to reduce before multiplying. You'll see you get 5 over 44. Now, the trap answer in this question is actually D. The reason that's a trap is because there's other ways in which you can make this selection. Remember, it doesn't say white, then red. It says white and red, which means you don't know the order that it's in, so you have to account for all possibilities. So the next thing we would do is we would say, okay, or probability of red then white. Now, you can do this out all the way and do the math, but I will tell you with 100% certainty that the probability of red and white versus white and red will be 100% the same because the stipulations surrounding that probability won't change. And just to prove that, we can say probability of red for the first selection is 3 out of 12 times probability of white is 5 over 11. If we reduce, this becomes 1/4. Notice once again 5 over 44. Remember what I said, when the word or is used, you add. So 5 over 44 plus, excuse me, that should be not 55, but a 5. 5 over 44 is 10 over 44, or 5 over 22, which is answer B. Now, the reason why combinations is a pretty smart way to go about probability in certain cases is because when you don't account for the order, let's say you said the answer was 5 over 44, it's going to alleviate the possibility that you're going to make that mistake. Now, of course, if you know that's just one extra step in the problem, certainly you can go ahead and use it, but I really think doing combinations with probabilities is pretty slick when it works. Obviously, when it doesn't, you can get into a lot of trouble. So what I want to do is I want to kind of change something up real quick here, and I'm going to clear the screen so we can kind of start fresh here. And I want to ask everyone a question, and I want to ask the question, if I changed what's being asked here from what is the probability of selecting a white and red marble to how many ways can the child select a white and red marble, And remember, this is now a combination question, so you can forget the answer choices for a second. What does everyone think the answer would be to that? I'll give everyone a minute to do that. Okay, so it is 15 ways. And the way you would do this, it's not that difficult. In fact, this has a lot to do with the fundamental counting principle. But if you wanted to be super technical, you could say, all right, well, there is 5 white marbles, and we're choosing one of them. And there are 3 red marbles, and we're choosing one of them. Because we must select both, we're multiplying them, so we have 5 times 3, which is 15. So that wasn't that difficult. As long as you know how to do combinations, that shouldn't have been that tough because you've done combinations like that before. So what we could call that, and let's get rid of my extra writing here. Now what we can say is, well, this is simply the favorable outcomes in our probability question. Now, that means all we have to do is get the total outcomes, which is really taking the grand total number of marbles we have and selecting 2. So we're taking out any restrictions that exist. As everyone recalls last week, the way I like to write these would be 12C2, 12 marbles, selecting 2. And if we use our box and fill method, we're dividing by 2 factorial. We have 12 times 11 divided by 2 factorial. We bring that in here. That's 66. So our grand answer is 15 over 66. 3 goes into 15 5 times. 3 goes into 66 22 times. So you'll notice once again we have the same answer. Now, I'm not advocating one method over the other at a question that's like this that I find pretty straightforward by just using straight probability. But what I'm hoping everyone is starting to see is that if a problem walks like a combination and talks like a combination, it can be solved like a combination. And that's why I rewrote the other problem, or this problem, to say how many ways can you select a red and a white marble. So what I want to do is I would like to expand on this idea here, just using actually a combination question that we did last week. So I want everyone to do this combination question out. You may even remember it from last week. We don't have to spend a ton of time doing the combination, but I want to show everyone how this question can also be morphed into probability, and then we'll get back and we'll do some straight up probability questions. So I'll give everyone 2 minutes on this. Like I said, this may be familiar from last week, but there's a big point I want to make. So start this now and enter your answer into the chat box. Okay, so obviously, like I said, this is not a combo, or excuse me, not a probability. This is a combination, but I'm going to show you very easily how this can be morphed into a probability question. So we're told that we're selecting 3 rubies. So that's 3 rubies, but we know we're selecting 5 jewels, and then that's going to be 5 non-rubies. Or excuse me, 2 non-rubies. We're selecting 5 total. So we know that we have 5 rubies, and we're choosing 3, so that's 5, choose 3. Do the box and fill. That's 5 times 4 times 3. Of course, that's the same thing. 3 factorial is the same thing as 3 times 2. So we get 10. The 2 non-rubies, we know there is 7. We're choosing 2 of them. So that's 7 times 6 divided by 2 factorial. And that ends up giving us 21. So because we're selecting the rubies and the non-rubies, we're doing 21 times 10, and that's 210. Now, here's what's important. If we change this question to say how many, instead of how many possible ways can he pick the jewels, if it said what, keep in mind, based on my change, the grammar is a little off here, but for all intents and purposes, what's pretty much being said is what is the probability of selecting the 3 rubies? Well, here's the good news. And I think this is pretty large for a probability question, so I feel like they would maybe make it a little bit smaller. The numbers would be a little smaller for you, but for argument's sake, let's say this is now a probability question. Well, here is your favorable outcomes. So really all we would need is to get the total outcomes, which is, selecting these 5 things with no restrictions. And we're seeing that we have 5 rubies, 4 emeralds, and 3 diamonds. That's a grand total of 12 items. We're selecting 5. So we would do 12 choose 5. So this is going to be, as I said, fairly large. 12 times 11 times 10 times 9 times 8 divided by 5 factorial, which is 5 times 4 times 3 times 2. We could do some canceling. And we get 12 times 11 times 6. We end up getting 792. So the total probability here without reducing is 210 over 792. And this, again, is a great example to see how a combination question can be morphed into probability, or vice versa from what I showed you before, probability into combination. As I said, in some of these questions, if you feel like you want to use straight up probability, in the traditional sense, you can. But I have found this to be a pretty great way to deal with a lot of these questions. So with that in mind, what I want to do is I want to dive right back into some probability questions. I'm going to be continuing to show everyone how to solve these using combinations. But as I said, you can use any method that you find works well for you. So let's start with this question, and I will give everyone 2 minutes to work through it. Okay, so that was about 2 minutes. I'm not sure if anyone got to the answer here, but if we are doing combinations to solve this, we're going to start off and we'll do the favorable outcomes first. The first thing to recognize is it's saying, what's the probability that she's picking exactly one girl? Now remember, there's 3 children being picked, so if there's one girl, that means there's going to have to be 2 boys. So as we normally would, if this were a combination and it said how many ways can one girl be selected when 3 children are selected, well, we would look at this in our separate girl bucket and boy bucket. So if we're looking at the girls, we're saying 4 choose 1 for the number of girls, that's 4. And then 5 choose 2 for the number of boys, which is, 5 times 4 over 2 factorial, which is 10. So we get 4 times 10, which is 40. That's the favorable outcomes. We'll denote it with a big F. The total outcomes is going to be the grand total of people that we have, which is 9. And we're choosing 3 because that's the total number of selections. Box and Fill says 9 times 8 times 7 divided by 3 factorial, which is 3 times 2. Cancel and cancel, we get 84. That's the total outcomes. We'll denote with a T. And finally, we just sandwich these together, giving us 40 over 84. Or in other words, this will reduce down. 4 goes into that 10 times, 21 for the 84. So it's answer choice B. So I want to do one more with everyone, and then I'll hand things over to Scott. But hopefully, as I said before, everyone's kind of seeing how combinations are playing a really big role in the problems I'm giving you. So I'll give everyone a few minutes. We can finish up with this problem here. Okay, so that was about 2 minutes there. So this is a scenario problem, and the reason I say that is we see the words at least, and we see at least 2. What scenario implies is that there will be different, well, more straightforwardly put, different scenarios, which means different events, which means we have to add. The reason it's scenarios is because it's saying at least 2 flowers will be roses, and we know we're selecting 3, so there's a possibility 2 could be roses where 1's a tulip, or all 3 could be roses. So if we're following the combination way of doing this, scenario 1 is going to be 2 tulips or a rose, and a rose, sorry. And we know that there are 3 tulips, so that's going to be 3 choose 2. Now, as I taught everyone last week, when you see something where this value is 1 less than this value, you don't have to do anything further. You can say that's simply equal to 3. And same with 3 choose 1. Anytime you have something against a choose 1, it's going to be the originating number. So in this case, 3, choose 1 is just 3. So we know that there are 9 ways to deal with getting the 3 roses, the 2 tulips. Oh, I think I wrote that backwards actually. 2 roses and 1 tulip. Glad I caught that. So now we just have to do the total outcomes. I'll put in F for favorable. Total outcomes is going to be the grand total number of flowers, which is 6, and we're choosing 3. So that's 6 times 5 times 4 over 3 factorial, which is 3 times 2. So that gives us 20. So scenario 1 is 9 over 20. Scenario 2 is going to be a little bit easier because it's all roses, so we don't have to deal with the tulips. So that's rose, rose, rose. There's 3 roses. Anytime you have something like 3 choose 3 or 5 choose 5 or 100 choose 100, the good news is it's always equal to 1. Even better, we know the total outcomes hasn't changed, so that's going to give us 9 total outcomes. So the probability of scenario 2 is 1 over 9, sorry, not 90, and, or excuse me, 1 over 20. That hasn't changed, so we have 9 over 20 for our probability is 9 over 20 plus 1 over 20 is 10 over 20, and that's reduced down to 1/2. So hopefully everyone's seeing that these combinations and probability questions can be very interrelated. The good news about that is once you know how to do the combination components of these, it's not going to be too long before you can do them with probability. From here, I'll pass everything over to Scott, and he's going to take you guys through some different types of probability questions the rest of the webinar.
Hey guys, Jeff, how's the audio tonight?
It's better, so we'll keep our fingers crossed.
Good, good. Hey guys, as always, thanks a lot for coming. Just remember a couple things about combinations. There are things that most people haven't really had too much exposure with in the past.
Scott, I lied. It's not sounding so great.
Oh, guys, you know what? We're changing office spaces, and we got a lot of tech issues going on. I'm not sure why it happens it's normally okay. It must be something with WebEx. So, Jeff, it's not going to be sufficient to carry on? Hold on, let me see if I can troubleshoot it. Just give me a sec. Is that any better?
Yes.
You're kidding. So that's better right there?
Yes, that's better.
Okay. Are you sure it's good enough to continue?
Yeah, if anyone has an issue with Scott's audio, definitely speak up, but from what I'm hearing, it sounds good.
Yeah, guys, if anyone is having a hard time hearing me, maybe pop in the chat box and Jeff can take over, but okay, cool. Yeah, if anyone has a problem, let me know. All right, cool. I'll carry on, Jeff. If anything goes from good to bad, let me know.
Sounds good.
Okay, great. So it just takes some practice, guys, and they're really not so bad on the GMAT. They seem big and bad, but the bark is worse than the bite. So what I'm going to do is I'm going to kind of piggyback a little bit on what Jeff did and go over some things with you guys that students tend to struggle with. And we kind of call it the probability of creating codes. And we'll kind of use codes loosely. We're going to look at maybe making some license plates, maybe looking at some product numbers in a home improvement store, all things that actually have some practical relevance. And I don't care, whether you use combination approach or a probability approach. Just to kind of stick with the theme tonight, I will probably use a combinatorics approach to helping you guys solve these. But at the end of the day, what you really should do on your own is you should do both methods, because the more ammunition you have, the more firepower you'll have come test day to solve these guys, especially when things tweak and get twisted a little bit. So just be forewarned, these are not easy, but they're not really hard either. So the reason why I say that is if you are a beginner, don't feel bad if you're like, wow, these seem pretty challenging, and they won't the more you do them. All right, let's give it a whirl. We'll shoot for about 3 minutes on this. Should be good. Let's start now. All right, guys, that was about 3 minutes. So we have this home improvement store, and it uses a 6-letter code to identify each piece of merchandise. Pretty common scenario for big companies that have physical inventory. The code can be created from any of the letters of the alphabet with the exception of H and D. So the only thing that's unusual in this problem is that any part of the code can be created from the letters H and D, any of the letters but H and D. So that means we have a total of 24 possible letters, right? Normally there'll be 26 letters, but H and D are excluded from being allowed in the code. So what's the probability of randomly selecting a piece of merchandise that has the code A, B, C, E, F, G? Well, the first thing I want you guys to see is there's nothing inherently special about the code A, B, C, E, F, G. It's just one particular code out of all of the possible codes that could be made. Okay. Now, there's a lot of really hard, really lengthy ways of solving this, and there's a couple really short, efficient ways. Now, I think I'll show you what I think is the most efficient way to handle a problem like this. And we're going to use the fundamental counting principle, which last week Jeff really explained to you guys was something that's really important. And if you forgot, remember the fundamental counting principle basically says something like, you know, if you have m ways to do one task and n ways to do another task, well, both of those tasks, the total number of ways those tasks could be done is m times n, and you can extend out to any number of tasks you want. Okay, so if you think about this here, each letter of the code could be represented by a box or a dash, whatever you want to draw. Right? So here are the 6 possible letters for a code. Picture, you know, a piece of merchandise, a shovel or something. And if you think about it, if we look in box 1, we just have to ask ourselves very simply, you know, how many different possibilities could exist here? And always remember, too, guys, we're trying to look at this through the eyes of kids, not through adults, because adults overcomplicate these things badly. Try and look for the simplicity within the complexity here. So if you just ask yourself, you know, how many different options could the store use for this first position? Well, it's 24, right? It could be any of the letters of the alphabet with the exception of H and D. Right? So 24 letters could go here. Now, for the second option, I mean, it doesn't tell us we can't repeat letters, which is something you need to be alive to and cognizant of, right? If they told you no letters could be repeated, that's a different story. But here, the step doesn't tell us that, so we could reuse any of those 24 letters there, right? So it could be 24 letters in the second part of the code, and 24 letters in the third part, 24 letters, 24 letters, and 24 letters. Right, because remember, each piece of merchandise has a 6-letter code. Okay, and there are 24 options for each part of the 6-letter code. So if you think about it, the fundamental counting principle would therefore tell us that there are this many possible codes that could be made. It's a lot of codes, right? It's a big number of codes. In other words, to make this more manageable, there are 24 raised to the 6th power number of codes that could be made. Right? And as Jeff's been telling you, probability is nothing more than the favorable number of outcomes divided by the total number of outcomes, right? So if you think about it, this one specific code is just that. It's just one code out of the 24 to the 6 possible codes. So if you were randomly picking merchandise, you would find that this is one possible code out of this big number of 24 to the 6 possible codes, and that's the answer. Okay, 1 over 24 to the 6th. Okay, so notice here we use the fundamental counting principle to make our lives a lot easier. and we use the very basic probability equation or formula, which is favorable over total. And we just looked at this from a very simple point of view. And that's the biggest trick with this probability stuff, is that the more simplistic you can make it, the better off you're going to be. All right, cool. So let's try another one. Let's try another one that's reasonably similar, but a little bit different. And we're going to go back to the same home improvement store. And be careful here because there's a difference in this problem, big difference. So let's give this guy a whirl, and let's try and use some of the skills we just learned. And we'll shoot for about 3 minutes starting now. So let's give this a whirl. So again, we have a home improvement store uses a 6-letter code to ID its merchandise, and we can't use the letters H and D. So as I said, we're piggybacking on the last problem to kind of give you a stepping stool to this one, which integrates in a new concept. So we know that we can make these 6 boxes to represent, in general, this code. And as we said before, normally there'd be 26 letters of the alphabet, but because H and D are going to be excluded, well, those guys can't be used. So what that means is we're down to 24 per option, right? So the first letter could have 24 options, the second letter could have 24 options, right? Each of these guys could have 24 different options. And because we know the fundamental counting principle, we can say, well, if you have 6 different things that each have 24 different outcomes, right, and we're putting these guys all together to create a code, well, therefore, we know that the total number of outcomes possible, or the total number of codes that could possibly be created, is 24 to the 6th power. Okay, now, we want to know what's the probability if we create either this code or this code. Now, there's some nuances with OR. We probably won't get into it too much tonight because it takes a little discussion, but one thing you have to make sure you understand is, you know, when do two sets overlap or not overlap? Here, there's no overlap between the R code and the P code, so to speak, because they're just different, a different letter arrangement. So we don't have to worry ourselves about any overlap. But if there were overlap between the sets, you have to be sure you remove the overlapping component. If you're using our course, that's something we'll harp on a lot in the probability chapter. That's important. That comes up a lot in the test. But here, there's no overlap. So notice, too, there's really nothing of significance about these two codes. They're just two codes that could potentially be made. Okay? So what we're going to do is, so let's just call this code 1 for simplicity and code 2 for simplicity. So the number of ways we could make code 1 is just 1. Right? There's only one way to form the letters R, T, V, M, N, P, and that's R, T, V, M, N, P, right? There's no other way to do that. So there's one way to make that code, and we know that there are a total of 24 to the 6 possible codes. So this now represents the probability of making merchandise code number 1. That's the probability of making merchandise code number 1. Now, merchandise code number 2, it's symmetrical. There's nothing different about it. So merchandise code number 2 is the same thing, right? There's only one way to make the code PNMACB. That's PNMACB, right? So one outcome out of a total of 24 to the 6 possible outcomes. Right, so that's now the probability of creating the second code. And because, so therefore, 3 little dots mean therefore, because we want the probability that the customer could randomly get either code, so A or B, 1 or 2, it would be 1 over 26 to the, or 1 over 24th to the 6th plus 1 over 24th to the 6th. Which is 2 over 24th to the 6th, right? Because we have a common denominator, we can just add those guys. So one key thing I want you to see and take away from this is that when you're saying or, we're increasing the probability right here, because if you just pick one of the codes, it's just one outcome out of that huge number of possible outcomes. But if you're saying code 1 or code 2, just intuitively we should expect that there will be a higher probability, right? And if any of you play cards or poker or gamble or go to Vegas, or just even know what card games are, right? So in a deck of cards, I mean, like, you know, you could have aces and kings, for example. Well, the probability of picking an ace or a king is, you know, obviously much higher than just the probability of picking an ace or just the probability of picking a king. So that's an important nuance because you never want to pick a lower probability on an OR problem than what you would have if you were just looking for one of the items individually. Okay? So hopefully this makes pretty good sense. So the fundamental counting principle is sort of the combinatorics aspect of this, just sort of in short form. And obviously the rest of the problem was the probability component. Okay, so let's try one. It's a little more difficult, but to be honest with you, none of this is too difficult. Let's look at the number of ways that we can create license plates and the probability of picking a certain license plate at random. All right, let's try it for about 3 minutes starting now. Okay, guys, let's talk about this. So it says in a certain state, license plate numbers are created with 3 digits followed by 3 letters. And so we can create this little box structure again, 3 digits and 3 letters for a total of 6 things, right, to be totally articulate here. So 6 things go into this license plate. So we have digit 1, we have digit 2, digit 3, and then we have letter 1, letter 2, letter 3. And if you haven't noticed, diagrams are really helpful for a lot of this stuff because a picture really is worth, 1,000 words or more when it comes to questions like this. So we're going to be careful here because neither the digits nor the letters can repeat. So that's obviously going to change a few things in the way in which we attack this problem. What's the probability of a car receiving a license plate with the code 478 SKL? 478 SKL. Hopefully that's none of your license plates. So if you think about it, what we're going to do is we're going to first ask ourselves how many ways can the, excuse me one second. Okay, how many ways can the first digit be made? Okay, so the first digit, if you think about it, could be composed from all of the digits from 0 to 9, and 0 to 9 is 10 digits, right? So that means that there could be a total number of 10 digits that would go into the first spot of the code of the license plate. Okay? Now, we can't repeat any digits, so for digit number 2, we're going to be less 1. Right? We don't care which one we used, but we're going to be less 1, which means that we'll now have 9 possible digits. Okay? And I think you can see the pattern here. For digit number 3, we're going to have 8 possible digits. Okay, let's also look now at the letters. So letters are going to drop by 1 each time as well because they can't repeat. So no restrictions other than that on the letters. So there would be 26 letters, right? We use 1. We don't care which one we use. But then we have 25 letters left. And then we have 24 letters left. Okay, in the key, this problem is good to illustrate this. It's always good to kind of scan the answers and see what's going on, right? It's really important to see what form the answers are in. Okay, this will help us a bunch, so not to sort of overshoot what they're looking for. So if you think about it, you know, we see the 25, 26, the 24 in there. We kind of just have to make our stuff fit what we see there. So we can see that 10 times 9 times 8, right, this part of it is equal to 720. Okay, and then we have times 26 times 25 times 24. Now, it's a funky number, but who cares? The test is full of funky stuff, right? And the good news is we don't have to multiply that out. Now, if you think about it, the code we're being asked to make, 478 SKL, well, it's just one code. There's nothing interesting about that code, except that it's just one out of the many thousands that could be made. Right? So if you think about it, the probability of getting that code is the number of favorable outcomes, right, which would be 1, divided by the total number of outcomes, which would be 720 times 26, 25, 24. And whatever that is, who cares, right? We're not being asked to simplify that any further. So that's the probability. So the key thing, guys, is as we always say, and this is a really important little piece of strategy before we let you guys go, is that, remember, practice does not make perfect. And I will promise you that. If you are practicing the wrong strategies, with the wrong questions, with the wrong techniques, with the wrong knowledge, with the wrong tools and tips and pieces of wisdom, you're never going to be any better next week, next month, next year. And unfortunately, in my opinion, that's what is one of the most maddening things about the GMAT, the GRE, whatever test you're studying for. You have to practice properly. And if you're doing nothing more but popping into these webinars, take the skills we gave you this evening and try and apply them on your own. And if you read someone's solution and it doesn't make sense to you and you don't like it and it seems wacky, there's a good chance it is. And when that happens, try and come up with your own solution. You don't have to do things the way anybody else does them, me or Jeff included. So if you don't like the way we're approaching these, there are many ways to solve these problems. These are great solutions, though, and I think you'll see that when you put them into action. But don't ever feel like because someone shows you a way to do it, you have to continue with that approach. Okay, guys. Well, we appreciate you coming very much, and we know you have much better things you could probably do, more fun on a Tuesday evening, but I hope this is very helpful for you. We'll see you back here next week. Jeff, did you have anything you wanted to conclude with? Okay, I think that's a no. So we'll look forward to seeing all you guys here next week. And if you have any questions, as always, let us know. Send us an email, whatever you need to do. Thanks a lot for coming and spending time with us.